Let's get going. Good afternoon, everybody. Welcome to another exciting afternoon of organic chemistry with your host, me, Dr. White. Now, I sent out an email. I'm going to be doing updates. I just got earlier some feedback from one of your colleagues that I think will work out good, what you should be working on. In case you're just doing this as a straight internet course and looking at the videos, this will keep you on track. Because what I've heard from other instructors is students fall way behind. And it's unlike when you're face to face and you keep on reminding them, do this work, you should be doing this, or you come to class, it's a little different. All right. One thing I didn't mention yesterday that I should have when I was talking about what are the best gas stations and brands of gas, one of the things that I found, I don't know if you're familiar with, is can you see the site, the gas buddy on your screen? And this is ChicagoGasPrices.com. If you're not familiar with it, it's a great tool. Notice I put in the zip code for ECC, and this gives you all the prices of the gas stations in the area. You put a zip code in, and it's amazing. Sometime in a 2 or 3 mile radius, gas prices can be as different as 20 cents a gallon. And this works. Now, I live in Schaumburg, and usually if we were face to face at ECC, I usually go to this Shell on McLean and Fleetwood. Before they opened up, I went to the Marathon right across the street. But it's easier to get in and out of Shell, and I know they're the best gasoline. But if I look in my area, you can see the prices. Some are higher, some are lower. And what's convenient, I usually go to Mobile on Spring and Goof, and there's a Shell in the area I sometimes go to. And it's amazing between here and there, even though ECC is in Kane County and I'm in Cook County, sometimes the prices here are cheaper than Kane and vice versa. All right, speaking about gasoline, remember yesterday I talked about alkanes, which are acyclic saturated hydrocarbons. I talked about octane, the octane number. Remember, when you leave my lecture today, think about organic chemistry. It's all around you. I stole that from SpongeBob. But anyways, next time you go by a gas station, think about half the weight of what they're selling you are alkanes, organic chemistry. All right. And one other thing, let me just show you. If you haven't seen it, here's the Chem 170 YouTube channel. And I posted yesterday's lecture last night. Usually starting next week, I'll be teaching at the other school. So I may be up to 20 hours, maybe less than that. Within about 12, 14 hours, I'll have the day before his lecture in Zoom. And here I have it. Notice the title. I have the week number, and here I have the date, which is year, month, and day. Now, if you look, I have other ones. If you want to get ahead, you can go back to week number 1 right here. Actually, I have 2 semesters. We'll go back to here, and you can find out I'm doing about the same thing. If you haven't guessed by now, I've taught this a number of times. And if you want to get ahead, you can just keep on looking like at week 2. Don't forget, every week in the summer is the same as 2 weeks in this case, the spring. All right, we're talking about how to name alkanes, and that's called nomenclature. And yesterday I talked about how to find the longest chain. And then once you do that, if you have things that are branching off, which we call substituents, and the main substituent is called the alkyl groups, and how to deal with those. And let's go back to that. And let me do one thing first of all, close a couple of things here. I don't need any more. All right. Now, the question would be, have a pen ready to go. All right. Everybody see the structure on your screen right now? Thank you. Question would be, what is the IUPAC name for this? I'll do this one, then I'll give you one to do. And notice I've done something different. Well, let's first find the longest chain. Now, not always is it straight across, doesn't have to be, but 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons straight across. Another chain would be 1, 2, 3, 4, 5, 6, 7, 8. Another chain, let's see how many colors I have to work with. 1, 2, 3, 4. And let's see if I have another color. Let's see how this works. 1, 2, 3, 4, 5. So those are all the chains. And what you do is find the longest one. And you have two main choices, 8 or 9. And hopefully all agree 9 is greater than 8. So the longest chain would be 9. Let's get rid of some of these excess numbers. And when you have a structure like this, you have to do that. I have to do it even at my level. You just have to figure out and count carbons. All right, so the longest chain is 9 carbons. And now, once we've done that, we can say, what's the name for 9 carbons? And hopefully you've all started learning this. 9 carbons from this table. Hint, you should memorize this. Hint, big hint. Start memorizing. How many of you remember what I wrote on the screen obnoxious number of times yesterday? Propane. And see how I burned it in you. And remember what the structure is, how many carbons in propane? And that's how repetition does that. No name, 9 carbons. So the root name is no name. Are we done? No, we have left over 2 branches and 1 carbon and 2 carbon. And now the other table hint, you should know, like a real big hint, are the alkyl groups. There's others, but these are the key ones. And a CH3, 1 carbon alkyl group is called methyl. A CH3, CH2, a 2 carbon group is called ethyl. which is what we have. So this is a methyl group right here. This is an ethyl. Now, IUPAC has a rule that alkyl groups or substituents with the highest alphabetical priority closest to the front of the alphabet get named first in order of the alkyl groups. So this would be ethyl, methyl. Now, I'll show you later when we get into rings especially, this can get pretty tricky. So don't tell anybody, but I'm not going to hold you to that rule for alphabetical order, which means I will always do the correct IUPAC rules because I expect myself to follow them. Otherwise, the IUPAC police will arrest me. No, there are no IUPAC police, but I will let you have another answer that I'll consider correct on test. All right, now, are we done? No. What carbons are the ethyl and methyl group on? Well, now you start from either end of the chain and number. And notice if we go this way, it's on carbons 3 and 4. But let's go this way. 1, 2, 3, 4, 5, 6, 7. This way, they're on 6 and 7. And you always number in the direction to give these substituents, in this case, alkyl groups, the lowest number. If you notice, the ethyl group is on carbon 4, so that's 4 ethyl. And the methyl group is on carbon 3. So this would be 4 ethyl, 3 methyl, no name. Say that 5 times quickly. No, you don't have to. And that's how you do it. Let's go back again. You find the longest chain, and you name it as if it were an alkane from the table 1 through 10, methane through decane. In this case, 9 carbons, no name. Next, you look at what's left over, the alkyl groups, which are substituents, and I'll never ask on a test what's a substituent, what's an alkyl group, but I will use those terms in the semester. Alkyl group is a specific type of substituent. The substituent are things that are left over besides the main chain. So now we have to number them. An important thing, remember, you always start from the end of an alkyl group, not the middle. Students make the mistake and say, oh, that methyl group is on carbon 1. Wrong. You can't. You got to start from the ends. And that's how you do it. Now, remember, how do I know how to put how many hydrogens in? Remember, there's 4 bonds to carbon. And I'll let you try this one. What would be the IUPAC name for the following molecule? And when you're done, give me a thumbs up. And you can use the emoji if you don't have your screen on. Okay, let's do it. And if I look at across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's one way. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's another way. 1, 2, 3, 4, 5, 6. And there's one more. If I do this carbon, this carbon, this carbon, it's only 3. So you have 9 starting from this carbon, 10 going across, and 3. And I hope you all realize 10 is the largest number. Let me clean up here. And therefore, the longest chain is 10. And that's decane. Hopefully you'll be memorizing this chart. So the root name is decane, 10 carbons. As soon as I say decane, this is all spoken for. And we have, look, a substituent. It has 3 carbons, 1, 2, 3. And notice the center carbon, this one is attached to the chain. And if we look at the chart for alkyl groups, we have 2 possibilities for 3 carbons, N-propyl when it's to the end, and isopropyl when it's to the center. And in this case, it's to the center, so that's an isopropyl group. So this is now isopropyl. Decane. And are we done? No. What number is the alkyl group on? And again, you count from either end. 1, 2, 3, from this 4, 5, 6, 7. If I start from this end, it's on carbon 4. If I start from this end, it's on carbon 7. And you always use the lowest number. So this would be 4, let me get the right color ink, 4 isopropyl decane. I just remembered back at this example right up here, since they're not holding you to the alphabetical order, if you had put down 3-methyl, 4-ethyl nonane, I would have given you correct all points if this was 3 points each, but I'm always going to write the IUPAC name, and that's how you do it. Now, one of the things I talked about yesterday was how to do well in my class, and that's practice. Remember the example with the bicycle? So let's just do a real quick thing. Nope, I don't have it open. So I better open it up. All right, why is my, there we go. I've got so many things running on this computer that it sometimes slows down. Now, everybody see on your screen, practice chapter 2, practice alkanes practice problem. This is in D2L. In the contents, you'll see a folder called practice problems. And these are for you to practice on your own. Notice number 1, I'm not going to do them now. I should finish today this chapter, and I'll go through this probably on Thursday if you have any questions. But notice I have part one, how many carbon atoms are in the longest chain for you to practice. And I was even so nice, I didn't even put in the hydrogen so you wouldn't get confused. Made it easy for you. And then notice, give the IUPAC name. Then I have various molecules for you to practice on. And then we'll get into rings. All right, let's do one more important thing. Let's look at the following. And this molecule right here, the question would be, give the IUPAC name for it. So let's do it. What's the longest chain? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And this would be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. So the longest chain is 6. And I'll call this right here on a test. No, you don't have to circle things. I'm doing this to help you understand what I am doing. When I do nomenclature, no, I do this in my head, but not on a piece of paper. So 6 carbons. You look here is hexane. So the root name is hexane. And we have 2 of the same group. Oh, look, it's your old friend, the methyl group. How do we say 2 in organic? And the answer is di is 2. The prefix tri is 3. We have 3 of the same group. And 4 is tetra. And I've never used that other than in a very awful joke, which I won't tell you. It's just not funny. And so I have a methyl group, and there are 2 of them. So I use di. So it's dimethyl. This is all lowercase, but I have sometimes capitalized things, or if I were keyboarding it, it would be all lowercase. So I have dimethyl. Whenever you see di for an alkyl, 2 alkyl groups, that means you need 2 numbers. And if I come over here, this would be 1, 2, 3. If I start from the other way, 1, 2, 3, 4, 5. You use the smallest numbers for the alkyl groups. That's the IUPAC nomenclature rules. Remember, IUPAC stands for the official. You don't have to know it, but I like to say International Union Pure Applied Chemistry. So I think it sounds cool, just like those of you old enough to remember the man from Uncle. Uh-oh, I just did a generation gap on all of you. Sorry. But anyways, it's on carbon 2 and 3, and you use a comma to separate the numbers. Otherwise, you have the number 23. So this is 2,3-dimethyl hexane. And that's how you do handle more than one of the same alkyl group. All right, why don't you try this one? What would be the IUPAC name for the following molecule? 3 points each. And when you're done, give me a thumbs up. All right, everybody done? Or you still need more time? All right, let's do it. All right, what's the longest chain? And if I take my cursor like this, 1, 2, 3, 4, 5, 6, 7, 8, that's one chain. 1, 2, 3, 4, nah, smaller. 1, 2, 3, 4, 5, 6, that's smaller. 1, 2, 3, 4, 5. So the longest chain is 8. And if you look at the table for alkanes, 8 carbons is octane. And now, as soon as I say octane, the root name always goes at the end. On the right, I've spoken, all these carbons that are circled are spoken for. And we have left over your good buddy, the methyl group. There are 2 of them. So that would be dimethyl octane. Now we need a number. 1, 2, 3, 4, 5. We start from this end. 1, 2, 3, 4, 5, 6. And you always give the alkyl groups the lowest numbers. Therefore, 3 and 5. Since there's a dimethyl 2, remember di means 2, tri means 3. And therefore, it's on carbons 3 and 5. So that'd be 3,5 dimethyl octane. Let's do one more. Whenever you have 2 groups, you have like a di, you need 2 numbers. That's a pretty molecule. Now you know I'm an organic chemist. And the question would be, what's the IUPAC name for the following? And when you're done, give me a thumbs up. We were face to face. I'd be telling people, first I could see when people are done. I also tell them, look up and smile. All right, everybody's done. What's the longest chain? 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. The longest chain is 4. And the name for a 4 carbon alkane is butane. And I can pick any way I pick 4 carbons, I'll still get the same answer. That's the beauty of IUPAC nomenclature. So that's butane. Look what's left over. 2 methyl groups. Well, I know how to do that. That's dimethyl. Now, what carbons are they on? 1, 2, 3, 4. I don't have to need that. 1, 2, 3. So you either have carbon 2 or 3, which is the lower number 2. Now, if you just put this, it'd be wrong because you need 2 numbers, even if they're both on the same carbon. And the proper way would be 2,2-dimethyl butane, which is why I gave this example. So when you have 2 alkyl groups that are the same on the same carbon, you still need 2 numbers. Because if I only had 1 number here, like this, dimethyl, well, I know where 1 is, where's the other? And the beauty, and it is a beautiful thing they did, of IUPAC nomenclature is there's never, ever, ever any guessing. And that's how you do it. Any questions? Remember, I said it yesterday, I said it in the email I sent out today, I'll say it again. In my course, in my life, in my universe, there's no such thing as a dumb question. Always feel comfortable asking questions in my class. All right, let's move on. Now, I've already covered this. The main chain is numbered in such a way that the first substituent encountered along the chain receives the lowest number possible. Each substituent is located by a name and its number the carbon is attached to. When two or more identical groups are attached to the main chain, prefixes such as di, tri, and tetra. I've never used tetra in my whole career, other than there's a really, how should I say, poor joke, not poor in the sense of offensive, just not that funny unless you're an organic chemist. That's tetra methyl chicken wire, which I'm not going to spring on you. Anyways, and every substituent must be named a number. If two or more different types are present and listed alphabetically, that except that the prefixes di and tri are not used for alphabetizing, also N and iso are not used. So that's why I'm staying away from that rule, number 6, about, and punctuation, I'm not going to grade on. If you notice between numbers and letters, there should be a hyphen. Between numbers, there should be separated by a comma. And I'm not going to, there should be no space between the last substituent name and the name of the parent alkane. Well, guess what? I'm not going to grade that. I'm not going to be sitting there with a ruler and say, oh, look, you're 5 millimeters apart. That's too far. I'm going to take up that. I don't do that. All right. Now, the halogens are other substituents, and that's fluorine, chlorine, bromine, and iodine. I'll talk more about them when we get into aromatic compounds. And we've already done the IUPAC names. By the way, this let's hold off on. But fluorine is called a fluoro group. Chlorine is chloro. Bromo, bromine is bromo. And iodine is iodo. And you'd just be like a methyl group. But while I'm here, let me do a little something. Time for Dr. White's story. This is called carbon. This will never be on a test. This is a common name, and I'll teach more in later chapters, other common names. The IUPAC name would be tetrachloromethane, which is why I don't, tetra, because everybody calls it carbon tetrachloride. That's about the only place I've seen this. And this is called chloroform. Now, when you replace hydrogens on an alkane like methane, which you should know, which is natural gas and was quite flammable, it makes these not inflammable, non-flammable, I don't know if that's the right term. They don't burn that easily, like almost not at all. And a couple things. One time when I was making a call with the salesman to a customer, I had developed a fire retardant, a resistant urethane foam. As one customer we went to see, he had a collection in his office, it was the CEO of this company, of very old fire extinguishers. And I mean old. And one of the ones, he opened up a box, and there were these glass spheres filled with carbon tetrachloride. And back about the late 1800s, early 1900, they used those. If you had a small fire, you took the ball and you threw it at the base of the fire, it broke. The carbon tetrachloride won't burn under those conditions, and it smothered the fire. There's one problem with carbon tetrachloride and chloroform. They are some of the worst carcinogens around. And that's one reason they're not used. The other reason I brought that and other halogenated hydrocarbons, molecules of carbohydrate, in this case, with halogens like chlorine or bromine, but mainly chlorine, have been used in the past, not anymore to my knowledge, I might be wrong on this, as the solvent in dry cleaners. And back about the 1940s and 50s, and I don't know when it stopped, in parts of northern Illinois, Chicagoland, dry cleaners who wanted to save money, and they had the, say, carbon tet or chloroform was used like you would use water in your washing machine, but got dirty enough they can't use it. Instead of paying to have it hauled away, they go across the street or down the road where there's an empty field and dumped it. And Chicagoland were some of the most dangerous places, pollution-wise, sites by old dry cleaners. When I bought this house, I checked to see was there ever a dry cleaner nearby, and luckily there wasn't. Was that something you should be aware of? All right. Now, we learned about the alkanes. And before I go into the alkanes, there's one thing I should cover now. I could wait till later, but I think it's better to do now. On a test and in real life in organic chemistry, there are two nomenclature skills you should have. One is, as we just practiced, here's the name, here's the structure, give the IUPAC name. The other is draw the structure. And you'll see I write those 3 points each for a reason. Hint, hint, wink, wink, say no more. And if I were to put like on a test, something like this, draw the structure for, and if I were to put down three-methyl nonane, how do you decode this right here to know what to draw? Well, in organic chemical names, how do you decode it? You always start from the right and move left. So the first thing I see is nonane. And hopefully you've learned that table. Nonane is 9 carbons. So I'm going to draw my 9 carbons. I wait until last to put in the hydrogens. Next, I see going this way, methyl group. I know that's CH3. Where is it? On carbon number 3. Now, this is important. 1, 2, 3. There's my methyl. And I know there are 4 bonds to carbon. And since I've been doing this a few more weeks than you have, I can go real quick. And that's it. But wait a second. What if I did this? I started, this is 1, this is 2, this is 3, my methyl group. And the question is, what's the right answer? Roman numeral 1 or Roman numeral 2? I better be careful. I learned about a year or two ago that my students in general chemistry were never taught Roman numerals. Sad but true. But anyways, the answer is they're both correct. How can that be true? Well, most students say, oh, you're writing molecules on a piece of paper. They're stuck there. No, just like this pen or my models here, which can move around, molecules are always rotating. So the example I just showed you for the IUPAC name is, you think about this, here's my hand right here, my left hand. If I said, close your eyes, and while your eyes were closed, I went like that, and I said, oh, look, it's something different. You say, oh, come on, you just rotated 180 degrees. And that's all I've done on the piece of paper I just showed you on the whiteboard. One, Roman numeral one, if you rotate it 180 degrees, you get Roman numeral two, which means they're identical. And which one is correct on the test? And the answer is both. And that I can say that because I have at home here in my house a piece of paper signed by the president of Board of Regents, chairman of Board of Regents of Michigan State University, that I know this stuff, otherwise known as my PhD diploma. So there's always two different ways how to draw it. Either one are correct. And let me have you try one. Why don't you draw the structure for 3-methyl heptane? Have fun. By the way, if I say fun enough times, you might believe me. All right, I think everybody's done. So how do you decode this? You start from the right and move left. Heptane, if you look at the chart, that's 7 carbons. And I have a methyl group, and you know that's CH3, and it's on carbon 3. So I'll do this 1, 2, 3. I could have started from this end too, but I won't for this example. You could do either way. And now I know there are 4 bonds to carbon. Remember, that's your friend. This first carbon has 1 bond, 4 minus 1, 3. This has 2 bonds, 4 minus 2, 2. 1 bond, or 3 bonds, 4 minus 3, 1 carbon, 1 hydrogen, and I'll fill in the rest quickly. And that's how you do it. And there are plenty of practice problems for you to try both of these. Now, one thing I should mention, how many of you have ever been in either a 4 or 5-star restaurant? Years ago, there was a great one in Wheeling called La Francais. It took months to get a reservation, and it was fabulous. I ate there once, and the price was as good as how many stars. But nomenclature in organic chemistry, which is important, is like going into a 5-star restaurant and ordering plain white toast, dry. They'll keep you alive, but there's so many better things. And this is an important part of organic chemistry. But we'll get into more exciting stuff later on. But this builds the foundation. There's certain things for foundation that will help you succeed. And that's why I'm taking my time now. All right, now we've talked about alkanes, which are acyclic saturated hydrocarbons. Hydrocarbon molecule with only carbon-hydrogen atoms, saturated, only carbon-carbon single bonds, and acyclic, not in a ring. So let's talk about cycloalkanes. And those are the rings. Now, good news, it's similar to nomenclature for alkanes. The ring portion serves as the base name, but the prefix, and this is important, cyclo is used to indicate the presence of a ring. Now, let's do a couple basic ones first, and we'll get to other stuff. And the question is, give the IUPAC name. And that would be 3 points each. For this, if you notice, I don't see any carbons. Remember, every bend in a line is a carbon. So let's count. 1, 2, 3, 4, 5, 6. 6 carbons. If it was an alkane, not a cycloalkane, would be hexane. But because it's a ring, we use the prefix cyclohexane. And now we're done. And that's how you do rings. And if I look at it, we're just about ready for a break. In fact, let's take a break right now because we're seconds away from when I normally cut off. I hate the rush. Come back in 5 minutes. I can get up and do my stretching exercises so I don't cramp up. That happens when you get have mature muscles like me. I'll see you in 5 minutes. All right, welcome back, everybody. We're talking about cycloalkanes, and you number the benz in a ring to determine how many carbons. You name that as an alkane, and then you use the prefix cyclo. Now, one of the most common mistakes on test number 1 is students forget to put the word cyclo, and they just put down hexane for A, and I mark it wrong, give them 0 points. They get upset, and shouldn't I get partial credit? And I ask, have you ever taken anatomy and physiology? And a lot of Chem 170 students are planning on going into nursing, so they've taken that. I say, if teacher asks on test, what's this? And you put down a foot, should you get partial credit because they both have 5 digits? And the answer is, I bet not. I've never taken A&P. So don't forget, when you have a ring, use the prefix cyclo, like in cyclohexane, because when you leave it off, that's a whole different compound, and you get a big 0 points, because it's wrong. Please don't do that. All right, now, what would be the IUPAC name for the molecule on the screen? And when you're done, give me a thumbs up. All right. All you guys are working real quick. Thank you. And thank you for coming today. And if we count 1, 2, 3, 4, 5, every curve bend in a line is a carbon. That'd be pentane. But it's a ring, so we use the prefix cyclo. Now, how do we handle the following? Well, you name the root name as the ring. And therefore, it says 5 carbons. This would be, once again, cyclopentane. And, oh, it's your old friend, the methyl group. So in front, we have methyl, and we're done. Wait a second, don't you need a number? When there's one alkyl group on a ring, you need no number. If I were to say that's carbon 1, is this a different molecule? No, all I've done is rotate this. I don't know how many degrees, 360 divided by 5. And therefore, when you have it, and there are many ways you can draw this methyl cyclopentane. So with that in mind, what would be the IUPAC name for the following molecule? Remember, IUPAC means the official name. And when you're done, give me a thumbs up. All right. I did a bad job here. That's a little better. So this has 1, 2, 3, 4, 5, 6 carbons. That's cyclopentane. Good news on a test. My software does a nice job. Oh, look, this is something we haven't talked about. Because it's hard in an alkane, you got to draw a lot of carbons to put this. It's got 4 carbons. Notice 3 methyl groups to the center carbon, CH3, to the ring. And what do we call that? Well, if you look down here, what do we have? 3 carbons, methyl groups, the center carbon attached to a ring or an alkane, and that's a tert-butyl or T-butyl. This week, for next day or two, I'll call it tert-butyl, and then I'll be a lazy organic chemist and call it T-butyl. Either one is always correct on test. And actually, there shouldn't be a dash there, but that's a bad habit of mine. I do put one there sometimes. That'd be tert-butyl cyclohexane, and that's how you do it. Now, when you have 2 or more, and this gets a little tricky, 2 or more alkyl substituents groups are named and numbered the same as alkanes, except the alkyl group with the highest alphabetical priority is located at carbon 1. I'm not going to hold you to this, but you number in such a way always to give them the lowest numbers. And notice I have, if only one substituent is present, no number is needed. Let's look at this rule with 2 or more different alkyl groups. And hold on, don't write this. Let me use a better. All right, this is a better example. All right, first of all, we have a ring, it has 6 carbons, says hexane, it's a ring. Remember, use the prefix cyclohexane. Next, we have 2 alkyl groups. 1 carbon is methyl, 2 carbons ethyl. Now, you don't have to follow it, but I will. The ethyl goes first, methyl second if you did it. But now this is something I will not ask you to follow, but I will. And that is the alkyl group with the highest alphabetical priority gets the lowest number. And that's this one, 1. And you go either clockwise or counterclockwise to give the other alkyl groups the lowest number. And that would be, this would be 2. So this would be 1 ethyl, 2 methyl. Now, in reality, don't tell the IUPAC, please, I'm going to do this. And I will accept actually 4 answers for this. The one I've written is the correct IUPAC. If you put down 2 methyl, where the 2 methyl is first, then 1 ethyl, I would accept that. If you have the numbers reversed, 2 ethyl, 1 methyl, I would accept that. And if you have the names and the numbers reversed, I would accept that. But in real life, there's only one correct answer, and that's the beauty of IUPAC nomenclature, naming that there is that. And that's how you do with this. So let's have you try one. What would be the IUPAC name of the following molecule? And that is, in case you can't tell, this has 5 carbons in the ring. I was just thinking, if I was super lazy, I could just say, watch the videos from last semester. Guess what? That wouldn't be right for you people, and I won't do that. You can still watch them, but I won't. I'll still lecture. All right, everybody's done. 5 carbons, pentane, it's a ring. Don't forget to use cyclo. Students do that, and they lose points where they shouldn't. Please don't. So it's cyclopentane. I have a methyl group, your old friend now, but ooh, 3 carbons. And notice the ring is bonded to the end carbon of the 3 carbon alkyl group. What's that called? Well, if we look up here, there are 2 possible with 3 carbons, N-propyl and isopropyl. So the end carbon of 3 carbons is N-propyl, which is what we have. So that's an N-propyl group. Now here, the N you do not use for alphabetical, which is why I'm not holding you to the alphabetical rule for rings, and also alkanes. This is N-propyl P. This is M-methyl. I know my alphabet, and sometimes I don't. Methyl. And propyl. And since this has highest priority, this would be 1. This would be carbon 2. This would be carbon 3. So it'd be 1 methyl, 3 isopropyl. Let me just show you one thing. If I went the other way, 1, 2, 3, 4, notice the N-propyl is on carbon 4, and you always number in the direction to give all the alkyl groups the lowest numbers. I think you'll agree 1, 3 is lower than 1, 4. Now, on this one, I would accept 3 more answers. If you put 3 N-propyl, 1 methyl, I would accept that. If you have 1 N-propyl, 3 methyl, I would accept that. And there's a 4th one where you change the order, but that's how you do it. And that's how you do rings. However, when it comes to nomenclature, timeout, public service announcement from Dr. White. Don't forget, there's always 4 bonds to carbon. 4. Oh, I gotta get this finger fixed. 4 bonds to carbon. 4. Public service announcement out. Now, when it comes to nomenclature skills, there's 2 types of skills. One is, here's the structure, give the IUPAC name. The other is, here's the name, draw the structure. And by the way, don't tell me that I'm telling you this, but on the test, those are 2 types of questions for nomenclature you'll be asked. So if we look at this, let's do different color. I don't know. And the question is, draw the following molecule. So you're being asked to draw isopropyl cyclobutane. How do you do that? How do you decode this, know what to draw? You always start from the right and move left. Butane, oh, I know that's 4 carbons, but cyclobutane is a ring. Now you call that a square, but organic chemists call that a ring. And it's got an isopropyl group. Since it's only 1 group, you can put it on any carbon. This one, this one, this one, this one. Most of you will probably do that. Isopropyl, 3 carbons. The center carbon is bonded to the ring. And that's how you do it. And here's one for you to try. All right, when you're done, give me a thumbs up. I'll wait till everybody's done. I know one person's done. All right, I'll assume everybody's done now. They are. How do you decode this? You move from the right, move left. Hexane, oh, I know that's 6 carbons, but cyclohexane, I have a ring. With 6 side. I'm having a bad ring drawing day. Sorry about that. And butyl. Butyl is 4. And if we look at the chart that's in the lecture folder of Blackboard, of Long School, of D2L, you'll see N-butyl, 4 carbons, the N carbon is attached to the ring, which is what we have. And that's like, oh, these are fun. Let's do another one. And that's 1-ethyl 4-methyl cyclohexane. I see one person's already done, and the other person, give me a thumbs up when you're done. Thank you. All right, how do you decode this? You start from this way, hexane, 6, cyclohexane, a ring. Oh, on carbon 4, I have a methyl, carbon 1, I have an ethyl. Most of you, and you can draw the second carbon on this side or this side, doesn't matter because there's free rotation around that carbon bond between the alkyl group and the ring, so it swings around. This is carbon 1, 2, 3, 4, and a methyl group is this. Now, you could have also drawn it this way. And there are other ones. All I've done is rotated it 180 degrees. And that's the thing you have to remember. On a test, you can write it either way. And there are actually other ones I could write too. And luckily, I know all of them if they're right or not. And that's how you do rings. Wow, we've done a lot in the last 2 days. Now, the following, I'm going to turn the switch. Will this ever be on a test? Click to the off position. But I've been told sometimes you'll see this on certain entrance exams where they ask you questions about organic chemistry, and that's dealing with boiling points. That's the temperature in which a liquid boils, and later in the semester when we talk about distillation, I'll teach you what boiling really means. But the boiling point of alkanes rise as the chain length increases. You have 5 carbon chain and a 10, the 10 will have a higher boiling point. Now, the boiling point falls as the chain becomes branched, which makes it more, the book claims, spherical in shape. I know spherical, but when you have branching, that lowers the boiling point. If you have, say, N-octane or octane, and you have 2-methyl or 3-methyl heptane, they're isomers, The branched, more highly branched, will have a lower boiling point. And like I said, I'll never ask this on a test, but some standardized tests I've been told ask these stupid questions. It's interesting to know, but it's not anything I put on. Now, you can have different conformations, which is, and this switches off on this slide, where you have rotation around a carbon-carbon single bond. And if it was a 2 semester, I'd be going in more into this, but it's not. We're not. So I'm just going to briefly show you something. This is butane. And by rotating it like this, there are different conformations. And when these two methyl groups, CH3, CH3, are close together, this is a higher energy conformation. This is a lower because they're farther apart. Why? Because Mother Nature doesn't like crowding. If you were in a car, would you rather be in it with one person, or would you rather be in it with shoved together with 10 linemen from the NFL? Got my hockey hat on because I was watching the Canadians win, rooting for the Montreal Canadiens. But this is conformations because around the carbon-carbon single bond, that's what each of these lines or rods are, there's always free rotation. That plays a role in many things. In a ring, there are different conformations, and that plays a role in our hormones. But I just remember the switches off. Switches back on. An important part of this semester are reactions. And the beauty of organic chemistry and functional group reactions are we have general reactions that are the roadmap to tell us what products you're going to make. And let me do this. I don't know, what's the city I haven't been to in a long, long time or never? All right, here's one. I've never been to, not that there's anything wrong with it, to Spokane, Washington. And let's say I'm starting from Elgin Community College, ECC, get in my car, I want to go to Spokane. If I don't have a map, I don't have a GPS, I can't open up to get Google Maps or anything like that, what's the odds I'm going to get to Spokane in a reasonable amount of time? Zero. You're going to get lost. But if you have a map or you have a GPS, you're going to get there. It may take a little time to drive there, just all the way on the other coast, just about it. But that helps you. In organic chemistry, they're what we call general reactions. And they're for certain groupings or types of atoms, groupings in a molecule, or a couple of them, certain types of molecules. Whenever you see that, that's always going to be true. And this class, there are going to be about, a student a couple of years ago counted them. I think I teach about 52 general reactions. That, yes, you're going to have to memorize them. And I'll show you how to memorize them better than flashcards. Dr. White knows, and don't forget I have a PhD, about 400 general reactions. Do I know all of them? No, but I know the ones areas I've worked in quite well. So let's look at our first general reaction. And that is combustion. And combustion, like the combustion engine, is when you burn something. And that's the reaction of an alkane, and I should have also put here, which I will now, or cycloalkane. And you're reacting with oxygen, you need a spark, but I don't have to. And the chemicals you get are carbon dioxide and water. Now, important thing about this reaction is you also get heat, but the chemicals are just CO2 and water. Now, it's time for a nice gift from Dr. White. Unless organic chemists have to, and in this class you won't, we'll never have to we'll never have to balance the chemical equation in my class. The only time you do balance them is when you need to get charge weights, how much of things to mix together to react. So let's look at this reaction. Alkane or cycloalkane plus oxygen gives CO2 plus water. So on a test and in real life, you want to predict the products. And you would see the following. Give the product or products. Now, let me first, before I go into this, do a quick review. This is called a chemical reaction. At the base of the arrow are the reactants. Now, if you come from academics, which most of my life I worked in chemical industry, we don't call them reactants, we call them starting materials. And more likely than not, I'll call them starting materials because most of my life I worked in the chemical industry. At the head of the arrow, we call this the product or products. And therefore, if I ask you the products, and by the way, the plus sign is the word and this would be A and B react to make C. So let's look at our question on give the product or products that are following. Now we look at this and say, well, what do we know about that? That's only carbon, hydrogens, carbon single bonds. That's an alkane. Now it could have been, but it isn't, a cycloalkane. Ooh, look, oxygen, that's different. What do I get? And now this is what you have to memorize. And the answer is CO2 plus water. Heat is not a product in terms of a chemical product, and I'm not going to deal with that, but it turns out it's important. So if I have an alkane reacted with oxygen, what do I get? CO2 plus water. Do you have to balance it? No. That makes your life infinitely easier because organic chemists are lazy. And that's how you do it. Now, combustion, I will have to admit, is probably one of the most boring chemical reactions for organic chemists. However, in our society today, this is one of the most important. In the last number of years or decades, wars have been fought because of this reaction, because that's how we get energy for our car and other things. So I'm going to have you try one. And why don't you do B? Give the organic product or products for the following. No, I'm sorry, that's later in the semester. Give the product or products for the following. And when you're done, give me a thumbs up. All right, what do we have here? Oh, it's an alkane, butane. And we're reacting with oxygen. And the general reaction, which you'll memorize, hint, hint, big hint, gives you CO2 plus water. And therefore, the answer is I'm going to get CO2 plus water. And I'm done. Now, I should mention that some of my best students I've ever had in organic chemistry, Chem 170, always on a test wrote the general reaction underneath the reaction they were being asked to provide the product or products for. I can also say some of the top students I've ever had in Chem 170 never wrote that underneath. You can do it either way. But when I do that, instinctively, I look at what am I reacting, identify it, bring up the general reaction, know what the products are, and then write it down. And do I do that in real life when I do it? No. But don't forget, I've had a few more weeks of organic chemistry than you have. And it happens, I think, in this part of my brain that does go on. Now, let me show you one other thing. And this one you don't have to write down. Oh, by the way, in organic chemistry, the arrows don't have to be straight if you're running out of room. Now, the question is, what's the organic product or products are the following? And this is the chemistry instructor's favorite trick on a test. You put a big, scary molecule down there. If you don't know how to identify molecules, you get scared and say, oh no, whoa, what do I do? You go, eek, and you get the wrong answer. Hopefully you'll never do eek on my test, but just in case, if we look at here, we say, no, that's not a big, scary molecule. It's only carbon hydrogens and carbon-carbon single bonds, so that's an alkane. And it's reacting with oxygen. I could have had a cycloalkane. And you react that, you get CO2 plus water. And therefore here, guess what? You get CO2 and water. But that's the chemistry instructors, organic chemistry instructors' favorite trick on a test, and I'll have to admit I do it. You put down a big, scary molecule, because it's big and scary if you don't know what you're doing. If you practice it, no, that's an alkane. Oh, let's do one more. I gotta let you try one. And why don't you, what would be the product or products for the following reaction? I think everybody's done. So what do we have here? Oh, a big scary, no, it's a ring with this carbon hydrogen single bonds. So this is a cycloalkane. Reacting with oxygen, but it could have been an alkane. And what do you get? General reaction tells you CO2 plus water. And guess what? CO2 plus water. And that's what you get. And that's how you do general reactions. Now, it turns out in the alkanes for this course, that's the only reaction I'm going to teach you. For other functional groups, and alkanes aren't technically a functional group, but other things, I'll be teaching you more general reactions. Now, notice if you take octane, which I don't have written here, here I have butane, but if this were octane, you get CO2 and water. And a funny story, one time it was the cold winter, and I was driving with a friend who wasn't a scientist, and the friend we pulled up to a stoplight and looked at the car in front of us. I don't get too close. And my friend, she said, "Oh no, that car's leaking gasoline out the tailpipe." And I laughed. I said, "No, it's very cold." It was like 5 above at the time. That car must have just started out. The muffler and the tailpipe are still cold, and this oxygen reacting with the gasoline forms CO2 and water, and the water is condensing, and that's the liquid. And if we had more time, I'd say go out there with a lighter. No, you wouldn't do that, but it was water. So, all right, now, the important part of the way I teach organic chemistry is to relate it to the real world. Remember, next time you're out driving and you go by a gas station, remember they're selling good part of the way to the gasoline is alkanes. Anyways, I like to relate things to the real world. And the question is, excuse me, where do you find alkanes in our real world? I guess is it an oxymoron to say real world? That's not what I want. Is there, never mind, I don't want to get into it. And where do you find alkanes? That's a nice way of putting it. Well, first one is this one. And where do we find methane? That's natural gas, which we use to heat our homes, cook with, and also heat our water for hot water. Another one is propane. As I mentioned, that's stuff in the white tank that you use for your barbecues. If you have a gas barbecue that's not hooked up to the gas line, natural gas, they make those too, but that uses methane. This uses propane. Also, if you've ever worked in a construction site where they have these heaters that are portable, they use also propane, the ones I've seen. Now, when you get the longer chain, like octane, what product do you find? Gasoline. Now, if you go even longer chains, what's another product? Baby oil. Baby oil is essentially some perfume, a very small amount, but longer chain alkanes. Now, interesting thing, as you saw, alkanes are combustible, they burn. And years ago, I had this nurse in my Chem 170. She was going back to get her master's. They said, well, you haven't had organic chemistry for a while. You got to take it again. So she was in my class where I was talking about baby oil as alkane that's flammable. She says, yes, we teach new. She worked in needle, I'll get it out right one of these years, in a hospital, which meant dealing with babies and also special types of babies that are born very early. And they always warn parents before they left the hospital, you're going to use baby oil on your baby. Don't do it near candles or an open flame or cigarettes because it's flammable. And if you're into survival, a survival trick, one of them is it's always good. How can you make fire easily? Have something that'll burn quick in a Ziploc baggie. Have some cotton balls in your bug out bag, if you know what a bug out bag is. For a while, I was into survivalist. And after COVID-19 hit, I made sure my bug out bag was up to date just in case. These things at first looked pretty scary. But anyways, you put some baby oil on the cotton, put them in, and that helps it burn quicker. you need to start a fire. Now, there's something even better than that on cotton that's also flammable, and that's Vaseline. Also known as petroleum jelly, and that's even longer chain than baby oil. And finally, if you get really long chain, you have paraffin wax. And that's very long chains, and that's a white, slippery solid. And 50% of all candles, if they're good quality candles, are made of paraffin wax. Later in the semester, I'll teach you about the other 50%. And I'll tell you a story about where I had to go to I worked for a company that started out in the Netherlands making the other ingredient in candles. And they also made candles from the 1800s, but that's another day. But the next time you look at a candle, half the weight of that is alkanes. So on a test, I give an example of an alkane you use in your daily life, 3 points, and any one of these would be acceptable. Gasoline, baby oil, Vaseline, propane, or natural gas. Oh my goodness, guess what? We've got to the end of chapter 2, the alkanes. And what does that mean? 2 things. One, let's see, today's Tuesday. On Thursday, I will go through the alkanes problem set. If you have any problems or questions, ask. Am I going to go through every one? No. But I'll go through a couple selected one on each page. And if you want me to do one, ask. And you know what else that means? It's new chapter and functional group time. And now we're going to get into some good stuff. And what's that new chapter? Well, first of all, I got to open it up. And that new chapter deals with chapter 3, the alkenes and alkynes. What's an alkene? What's an alkyne? Switches on, by the way, he has been for a while. An alkene is a hydrocarbon, meaning a molecule that only has carbon and hydrogens that contains a carbon-carbon double bond. Alkene, hydrocarbon with a carbon-carbon double bond. And we write a double bond like this. There are 2 lines. Each line is a pair of electrons. So double bond has 2 pairs of electrons. Now, I didn't put the hydrogens in. I'll talk about that later. And the formula, which you do not have to know, is CnH2n for an alkene. And an alkyne is a hydrocarbon that contains a triple bond. And we use 3 lines between 2 carbons to show a triple bond. And that has 3 pairs or 6 electrons being shared between the 2 carbons. I didn't write this up here, I said it, but that's a double bond. So we're going to talk about double bonds and triple bonds. Now, not so much with alkanes, but starting now, there's something I should mention to you. And that is from here on out, you should always ask the question. If you don't know, ask me, why am I studying this stuff? Well, the important answer is you want to get a good grade because somebody told you you had to take organic chemistry. But really, why learn about this stuff? And that's when the fun part comes. And let's take a look at this. Why learn about double and triple bonds? Well, let's think about it. Double bond. I sort of gave it away on yesterday, but how many of you are familiar with carrots? And does everybody see the molecule on your screen now? Now, this is in the line drawing. Every bend in the line is a carbon. Every end of the line is a carbon. So these are methyl groups here. Notice here I have a double bond. Here I have a double bond. Do not write this down. This is called beta carotene. And beta carotene is the molecule in carrots that causes them to be orange. It absorbs all the light except the colors that make up combine to make orange. Now, it turns out your body can break down beta carotene to another molecule called the common name retinol. Retinol sounds like the retinas of your eyes. And it is an important chemical. And that's why they always say rabbits have good eyesight, like Bugs Bunny, because they're always eating their carrots. And that helps your eyesight. How much it does, I don't know. I'm not a medical doctor. I'm an organic chemist. Now let's look at another example. But before I do that, let me get out of here. You notice I'm in Wikipedia. I used to always say Wikipedia. My students would yell at me, no, it's Wikipedia. But anyways, Wikipedia has been so heavily policed by, in the chemistry area, I can't talk about other areas, by organic chemists like myself. And yes, I do have the credentials, and I have asked for changes when I ask, because of my credentials and my background, they get changed. That's been so heavily policed by chemists, especially organic chemists, that it's been years since I've seen any kind of major mistake in any posting dealing in Wikipedia with organic chemistry. Now that's beta carotene in carrots. It's an alkene, carbon-carbon double bond. And similar but not the same. This doesn't have the rings. This is called lycopene. And notice all the double bonds. Each place where you see two lines, that's a double bond. And this is the molecule that causes tomatoes to look red. By the way, red's Dr. White's favorite color. And this is, look at all those double bonds, lots and lots of them. And therefore, next time you look at a carrot or a tomato, you're looking at double bonds. And I'll talk more about triple bonds. One of them is in acetylene. Have you ever seen those super hot torches that they use to break into banks in the movies? Or if you ever go into a metal body shop, they use those to melt, cut metal, or it's one way to cut out a piece of metal. And that's a triple bond. And I'll talk more about it when we get into there. So alkene is a double bond, alkyne is a triple bond. And these are both unsaturated hydrocarbons. Remember, unsaturated hydrocarbon is a molecule that contains only carbon and hydrogens. That's a hydrocarbon. Unsaturated as either double or triple bond. And I'm not going to ask anything on the test on this spot. Hydrocarbons that contain less hydrogen atoms, and I'll talk more about this. You'll see this. We get in some reactions of alkenes and alkynes. Then alkanes, that's the unsaturated hydrocarbon. They contain one or more carbon-carbon double or triple bond or combination. And I'll talk more about this when you add hydrogen gas, H2, it will convert an alkene or an alkyne into an alkane. That means a double bond or triple bond will become a single bond, carbon-carbon single bond. Switch, I forgot to take this, put a big, everybody, put a big X through this. I forgot to take this out. Dienes, diamines, two molecules with two double bonds. I'm not going to do that. Oh no, let me go one more minute. I went over a minute, but I'll still let you out early. I'll let you out instead of 10, 15 minutes because I did an extra 5 now. But anyways, this chapter, now we're getting into the real functional groups. And the following chapters, there's going to be 3 or 4 areas I'll talk about. First, I'll go through where you find it in your real life, the new functional group. In this case, double and triple bonds, alkenes and alkynes. Next, I'll teach you how do you name them, dealing with the nomenclature of that functional group. Then we'll talk about this one you can't, but later on we will. How do you make them? And then how do you react them? With that, let's take a break. I'll see you in 5, and I'll be back. All right, let's get back to work. We're talking about double bonds, the alkenes, and triple bonds, the alkynes. Now, it turns out in organic chemistry, the end of a name will give you what kind of functional group you're dealing with. So let's talk about nomenclature of double bonds. Now, the ending ene is used to designate a carbon-carbon double bond. Now, I should have taken out of here, and Dr. White's lazy, and I didn't. When more than one double bond, which I'll never ask, 2 is a diene, 3 is a triene. I won't use that. Let's look at a double bond. Now, if you notice something is different here, and that's the 2 lines. That tells you have a double bond. Now, here on out, whenever you look at a molecule, you should look for what's different. What do I mean by what's different? What's not a carbon-carbon single bond or a carbon or hydrogen atom should get your attention like that. It doesn't come through as good in Zoom as it is in real life, but you should get your attention like that. That worked. So I have a double bond. Now, a double bond counts as 2 bonds. Let's look at this carbon right here. It's got 2 bonds from the double bond, but it always should have, carbon should have 4 bonds. So 4 minus 2 is why it has 2 hydrogens. If we look at this carbon right here, has a bond here, 1, plus the double bond, that's 3. Carbon should always have 4 bonds. 4 minus 3 is 1, which is why it only has 1 hydrogen. So remember, double bond counts as 2 bonds to a carbon. Let's rewrite this again. And the question is, what is the IUPAC name for this molecule? 3.C. Oh, I see a double bond. Now, the way you do it is you find the longest chain with both carbons of the double bond in that chain. In this case, there's only 1, 4. And 4 is butane. And for a double bond, you drop the ane and replace it with ene. Ene ending tells you double bond. So that would be butane. Now, are we done? No. You find what carbon of the 2 carbons of the double bond is closest to the end of the chain. And you use that number to give the location of the double bond. Notice this is 1, this is 2. If I went the other way, this would be 3. So which is smaller, 1 or 3? And the answer is 1. So this would be 1-butene. Let's go through how I did it. First of all, I saw, double bond. You find the longest chain with both carbons of the double bond. In this case, 1, 2, 3, 4. That's butane. But it's a double bond. Drop the ane ending at the end of butane and replace it with ene, butene, which I have there. Now you need a number where it is, and you find the carbon chain, 1 to 2 carbons of double bond that's closest to the end of the chain gets that number. If you notice, we start only at the end. This is 1, and this would have been the other way, 3. That's how you do it. Now the rest, if you have alkyl groups, you know this is 1, this is 2, this would be carbon 3 and 4, and so on. And let me give you one to try. Your turn. What's the IUPAC name for the following? Uh-oh. Sorry about that. I'm getting a show and tell ready for you. All right, let's take a look at this. First of all, when you look at an organic molecule here on out, and I do this every time, I look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen atoms. A double bond. How many carbons along this chain with the double bond? 1, 2, 3, 4, 5. That's pentane. But it's a double bond, and you drop the A and E at the end of pentane and replace it with ENE, pentene. Am I done? No, excuse me. I have to know which is the lead carbon closest to the end of the chain. Here it's 1, going the other way, 1, 2, 3, 4. So which is smaller, 1 or 4? And the answer is 1. And that's how you do it. That would be 1 pentene. Oh, let's do one more. And why don't you do C? I'm working you hard this afternoon. Let's get my bullwhip out. Oh, wait, it died. Dr. Whiteson's unusual weapons. Uh, when I was a kid, I always wanted to learn how to use a bullwhip, and I did. Unfortunately, my really good bullwhip died a while ago. I had a 16-foot bullwhip I could crack real good. All right, if you're done, give me a thumbs up. All right, let's do it. Look at the molecule, look for what's different. Double bond. How many carbons in the longest chain with both carbons of double bond? 1, 2, 3, 4, 3, 4. Either way, it's 4. That's butane. But it's in double bond, so I drop the A and E and put in, do what I said. Just had a brain freeze there. Put an ENE ending, butane. What end of the chain is the one of the carbons of the double bond closest to? This is 1, going the other way to be 3. So that'd be 1 butane. As soon as I say that, this is all spoken for. Are we done? No, it's your old friend, the methyl group. And what carbon is it on? This is 1. We already defined this, therefore this is 2. The methyl group is on 3. That's 3-methyl, 1-butene. Let me rewrite it. And in a whiteboard in a classroom, the same thing will happen. Which is why when you take a test, have a good eraser present and do it in pencil. And that'd be 3-methyl, 1-butene. let's skip this. I'm going to come back to it, this stuff in a second. And I'd like to talk about the pi bond. Now, what I'm going to show you for right now, I'm turning, will this be on the test switch to click the off position, but this will help you understand something very important about double and triple bonds. And a pi bond is one of the two bonds that make up the double bond. And let's talk about a double bond contains one pi bond, and the other one is called a sigma bond, like a single bond. And pi bonds are different than sigma bonds. Pi bonds you can break easy. Now, the following, I'm just going to go over real quick. It contains a hybridized sp3 of them, sp2, 1p orbital. Now, the bond angle in a double bond is 120 degrees, different than a single bond. And there's no rotation around carbon-carbon double bonds because of the p overlap, orbital overlap of the pi bond. Now, let me show you what that means. Again, switches off. This is a carbon right here in the center in a double bond. A carbon has 4 electrons that it can use to bond. Those are called valence electrons. And 3 of them are in what's called the gold sp2, and the 4th one is in the blue p orbital. And when you bring 2 carbons together, they share electrons. And they come together, overlap, and right here, this is what a double bond really looks like. The sigma orbital is like a carbon-carbon single bond, but then add the pi, and it's locked in space. You can't have rotation around a carbon-carbon double bond. It's locked. And that plays a very important role. And because of that, the double bond is called trigonal planar. It's flat in a plane, and the bond angles are like a triangle. And that's why it's called trigonal planar. Now, did I tell you how great of a job IUPAC did in their nomenclature? No 2 different molecules ever have been found to have the same name, IUPAC name, when done correctly. And 2 names different, you can't draw the same compound. Remember that. IUPAC has done such a great job. No 2 different molecules ever have the same IUPAC name. So let's look at an example now that we know about what's called the stereochemistry of a double bond. Here are my models. Notice they use these 2 lines, but if I take off a couple carbons, and this one, you can see how this carbon, the end of this and here, are in a plane. And unless I break the model, which I'm not going to, it doesn't rotate. If you have a carbon-carbon single bond, notice how it rotates, and you have what's called free rotation. Double bond, nope, it's locked into place, fixed. Now let's look at 2 more molecules to do nomenclature double bond. I've been pretty good, so I assume everybody can see my whiteboard. And now I'm going to show stereochemistry, where the atoms are located, because in a double bond, unlike a single bond, these are fixed. I'm going to do 2 molecules at the same time. It's 2 for Tuesday. Oh, that was awful humor. All right, let's call this A, one from column A and one from column B. Let's look at A. Now, even though this is bent, this carbon is bonded to this carbon, which is bonded to this carbon, and this. They're all part of the same chain. So 1, 2, 3, 4, butane. Let's a double bond, drop the A on the ending, put in E on the butane. What carbon of double bond is closest to the end? This is 1, this is 2. I went the other way, it'd be 1, 2. So this is 2-butane. Now let's look at B. Remember what I said, hold on. This is thirsty work. Remember, IUPAC has done such a great job that no two different molecules ever have the same name. Now, let's look at B. And here, oh, we've got 1, 2, 3, 4 carbons. That's butane. It's a double bond. I'll drop the E on the ending, butane. And notice this is on carbon 1. This is 2. Uh-oh. This is 2-butane. A and B are different molecules because they have different stereochemistry, but they can't have the same name. Relax. IUPAC knew what to do with this situation. And let's talk about the following. Let's talk about cis-trans isomerization switches on full blast. How many of you ever saw the movie This is Spinal Tap? If you didn't, it's a classic. It's not my favorite movie, but one part I do like is this rock band. They're saying, we're so loud, we have our amplifiers, which normally the dial goes up to 10, we turn them up to 15. And I always say, at this point, I just turn the dial up to 15, even though it only goes to 10. This is important. Due to no rotation around carbon-carbon double bonds, you can have what's called isomerism. And remember, an isomer are two molecules that have the same number of and same type of atoms, but different how it's put together. And cis means the same side, two either groups or atoms or combination are on the same side of a plane of a carbon-carbon double bond. I'll show you this in a second. And trans means they're on the opposite side of that same plane. Let's go back and look at our example. And before I do that, let's put down here or up here, cis. And let's look at A. If I were to put a plane, this dotted line, think if I laid a pencil down. Notice the hydrogens here, or the methyls, even though it's part of the chain, you think of them in terms of cis or trans, they're on the same side. They're both below the line. And this is cis. So the proper name for A is now cis-2-butene. Now, if we go over to this one, B, here's my same plane, or if I laid a pencil right down here, notice the hydrogens or the methyls are on opposite sides, and that's trans. So A is cis-2-butene, B is trans-2-butene. About 20 years ago, IUPAC said, oh, let's change this to German to E and Z, E and Gangen together, E and Gangen opposite, Z zusammen together. And the organic chemistry, everybody said, we don't like that. So IUPAC kept both, but most people still just use cis and trans. For certain situations, Z and E work well, but I'm a cis and trans person. Oh, by the way, how many ever heard of trans fats are bad for you and cis fats are better, healthier for you? Did you hear about that? If you did, they're talking about a double bond in the fat and are the hydrogens on the same side or opposite side. By the way, just so you can see they're really different molecules. This is cis. See how the hydrogens uh, these are hydrogens are below my hand, the plane like this, or these methyl groups are above. I go like this, you can't see it. And here, it's the same molecule, so I better fix it. Notice the hydrogens are opposite, or these methyls, and that would be trans. And they're locked in place. You can't rotate it unless you break the model, which I'm not going to. And that's cis and trans. And it plays an important role in a number of places, like in our body. Why is that a factor? I have no idea. But medical science has proved that that's why it is for cis and trans fats. Now, later in the semester, we'll get into fats and oils, and I'll explain the specific molecules that cause that. So now that we know cis and trans, oh, one other thing I should point out, the molecules that I wrote at the beginning, I didn't want to cover cis or trans yet, so I didn't show stereochemistry, where I wrote it like this. And notice this I wrote down as 1-butene. And the examples I had you were all the double bonded carbon 1. So I didn't want to talk about cis or trans yet. Now, when you have two of the same atom or group on one of the carbons of double bond, notice this has two hydrogens on this carbon. You can't have cis or trans isomerism. Therefore, you don't use cis or trans. But other than that, you always do. And let me do this molecule. Question is, give the IUPAC name for the following. And you look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atoms. And, oh, a double bond. How many carbons in the longest chain with this double, both carbons double bond? 1, 2, 3, 4, 5, 6. So I could have come down here, would be 6. So that's the longest chain. 6 is hexane. But a double bond, remember, A-N-E ending of hexane goes to E-N-E ending. And therefore, this is hexene. Next, what carbon is the lead carbon of the two carbons double bond closest to the end of the chain? This is that 2. If I went the other way, 1, 2, 3, 4, which is smaller, 2 or 4? Hopefully you all say 2. So this is 2-hexene. Next, can you have cis-trans isomerism? And notice this hydrogen are on opposite sides. And remember, cis means same side, trans, opposite side. So this is trans. As soon as I say trans 2-hexene, this is all spoken for. Am I done? Oh no, we have an alkyl group. Our friend, the methyl group. And what carbon is it? Remember, we just said this is carbon 2, therefore this is 3, 4, 5. It's on carbon 5. It's 5-methyl trans 2-hexene. And that's how you do it. Wow, that was a lot. I'm going to share the fun, let you try one. And there's one for you to try. What would be the IUPAC name for the following? Closer we get to the 4th of July, the worse my hydrogens look. If you buy that, I've got a bridge in downtown Chicago I can sell you. All right, don't forget, give me a thumbs up when you're done. All right, let's do it. Look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention like that. And a double bond. How many carbons in the longest chain with double bond? 1, 2, 3, 4, 5. Down to here would be 6. Here would be 6, 7. I hope you all agree 7 is greater than 6. So 7-alkane is heptane, but it's a double bond. So I'll drop the A on the ending and convert it to E on the ending. Heptene. What carbon is it on? If I start from this end 1, it's on 3. If I start this end 1, 2, 3, 4, which is smaller, 3 or 4? The answer is 3. 3-heptene. Next, we have cis-trans isomerism. And notice each carbon has a hydrogen, and they're on the same side of this plane I just showed right here. You don't have to draw that in, but I'm trying to show you how to see it. Same means cis. So we're cis 3-heptene. And as soon as I say that, this is all spoken for. We have a methyl group. And that's on carbon 5. So it's 5-methyl cis 3-heptane. Say that 5 times faster. Ooh, I got one more for you to do. Everybody know what that is? It's transparent. Hydrogens are transparent. You can all moan and groan now. I got to keep them clean for this class, any class I teach. All right, and that's how you do double bonds in a cyclic compound. And that's how you do trans, cis, and trans. And that's the importance of the pi bond. And by the way, I didn't do it, and I should. You should know that a double bond contains one pi bond and one sigma bond. And we'll find out later the chemistry of double bonds involves breaking that pi bond, which is quite easy and fun to do. So I didn't write it down. I apologize. You should know that a double bond contains one pi bond and one sigma bond. Again, hint, know this. Double bond, one pi bond, one sigma bond. There's something, unless I have in a later slide, I don't see it. But let me go through a couple other common names. Now, they're common names that were in use and still are in use before IUPAC came out with their rules. And ethylene the IUPAC would be ethene, since you can't have two ethene, you don't need a number, but everybody calls that ethylene. Propylene, whoa, what is going on here? Is this molecule, and these two you do not have to know. But one I would like you to know, when we get to triple bonds, is acetylene. When it comes to, and that's a triple bond here, let me write it a little better. And triple bond, you have three bonds. Notice this carbon here has three bonds. 4 minus 3 is one hydrogen here. Now, when it comes to common names on test, I will never ask you, what is the common name of a structure? I will ask you, here's the common name, draw the structure. And why am I doing that? Because you're going to encounter more often than not common names on ingredient labels for things. And this is something, a benefit of taking my class. By the end of the semester, you'll be able to pick up things that you use in your daily life. If you want to, you can know what the chemical structures of those organic molecules are. Or if not, I'll teach you how to use the internet also. Now, switches off for this, but an alkyl group, when you have CH2 double bond CH attached to something else, we call that a vinyl group. I've heard that name before. How many of you have heard of vinyl floors? And those are made from molecules that contain a vinyl group. Here's another one. Again, switches off. This molecule is called it's called vinyl chloride. And it's used to make a compound called polyvinyl chloride, otherwise known as PVC, and that's the white pipes in your bathroom. So next time you look under your sink and you see those white pipes, that's organic chemistry. I'll teach you later this semester more about polymers. Now, what I don't have, and I better go and do, I might have it, but let me, hold on one second. Let's take a look. No, it must have fallen. The dreaded, I lost the slide virus got me. Well, good news. I can do it on the whiteboard. Let's look at a double bond in a ring. Notice you see two lines, that's a double bond. Now, in this class, and I should have mentioned it earlier, unless you get up at my level, and even that is rare, most of the rings you're going to deal with are 4, 5, and 6. I've never encountered anything higher. I've seen some papers, someone do academic papers where they make larger rings, and they've used them somewhat. But in industry, in our daily life, you don't see them. And therefore, I'm not going to talk about them in class because we're not going to deal with them. But 6 is. So how do we name this compound? Look for what's different. Double bond, alkene. If we were to name this, how would we name that? Well, it's 6 carbons, hexane. It's a cyclohexane, but double bond, ANE ending is dropped and replaced with ENE ending. And this would be cyclohexane. When there's nothing else on the molecule, you don't use the number, because always, and even if there is something else, one of the carbons of the double bond in a ring, when there's no other functional groups, which will be true most of the semester, will be 1, the other will be 2. So when you have a ring with a double bond, you name it as a cycloalkane, drop the ANE ending, replace it with ENE, and also for the rings, we're always going to encounter 4, 5, or 6. The double bond will always be cis. And everybody knows that if you know IUPAC rules, which you are learning that. Therefore, we never have to put cis or trans in a ring. Because until you get to, I think once, long time ago, I saw someone had a paper where they synthesized, meaning made, a ring with, I don't know, 18 or 7, 15, 16 carbons. I don't remember how many lots, and had a trans double bond. It was one of those papers where the person who did it was, ooh, look what I could do. And you wonder, so what? Now you have bragging rights, but I don't see how that's applicable to stuff. That's when I was an industrial organic chemist work. I still do. So let me have you try one. What would be the IUPAC name for the following? It looks like everybody's done. You look for what's different. A double bond. And it's in a ring. How many carbons? 1, 2, 3, 4, 5. And that would be cyclohexane, but it's a double bond. Drop the ANE, put in, what did I think? Brain freeze. Cyclopentane, drop the ANE, put ENE, no number, I'm done. Speaking about done, since I went a little over the break, the last break, I'm done for today. Isn't it amazing? Time flies when you're having fun with organic chemistry. At least I hope it did for you, it did for me. With that, I'm done. I'll see you tomorrow. And tomorrow will be Wednesday. We'll have our first lab. If you go to the assignment area, it's there for you to download. as a PDF or a Word document, and we'll do that. Plus, we'll continue on with the material here. And with that, I get to say, gang gesund, goodbye. And for those who are familiar with the Belgrade Hillbillies TV program, remember how Granny used to do this at the end? Or did I just do another generation gap? It's on YouTube, I'm sure. With that, gang gesund, be healthy. I'll see you. Bye. Thank you, Johanna.